Good morning, everyone. Today, I will discuss about the organic chemistry topic for the any bachelor degree and PG courses, common and important topic, and also the BTech and of different IITs. Uh, Theory is called crystal field theory or octahedral complex. There are tetrahedral complexes. Thus, here put octahedral complex. Thus, Murshidabad College of Engineering. This is the first chapter the series of crystal theory, and they will have the introduction field why we have taken this crystal field theory, because in 1929 and 1935 two scientists, Hans Bethe and Van Blake, both independently have investigated that there is a need of another theory, because valence bond theory, the old one, cannot interpret something. Which one cannot interpret is given here, but they have proposed that they have to replace with a theory. This is they called crystal field theory or CFT, and it replaces valence bond theory for interpretation of chemistry of coordination complexes. Why valence bond theory has a failure? Because they have not given about the details of tetrahedral and square planar complexes or distortion complexes, polar complexes, and optical spectra, and temperature dependence of the magnetic process. This is a reference from where I have taken that JDL, etc., etc. As we know, when a metal is introduced in a ligand, the electrostatic interaction between ligand and metal have a two type. D orbital aligned along the octahedral axis will have take the most. More directly, the ligand attacks the ligand orbital, higher the energy of d orbital. In an octahedral field, the generacy of the 5d orbital is lifted. Is in octahedral field, there is no degeneracy of the orbital present in d clusters XYZ. How their degeneracy is lost, energy is different for different elements is will be discussed here. As we know, there are five types of d orbitals. When we have a metal, the electron cloud will be as simple as that. When we have dxy orbital, is it is x and y, then it is along the axis. Is yz, it is also along the in between the axis, and in between the axis. Dxy, yz, xz. When we take dx square, y square, and dz square, both are along the axis, that is x and y. And also it is in z. So 5d orbitals are there. There are two type. First one is three orbitals are there, which are three orbital are there, which are in between the axis by z, and also there are two orbitals which are along the axis. This is the type of the d orbital present. And when this metal, suppose you have taken this metal, where there is no field, it is in the low temperature, that is low energy, that is You can find here is the energy, this parameter. When they are filled in a spherical sphere, their energy becomes higher. So degenerate 5d orbital is an isolated gaseous metal ion, and spherically symmetric metal field of ligand negative charge. All degenerate 5d orbitals are raised in energy due to repulsion from ligand. So from ligand repulsion, their energy raised. And this is the total XY 5d orbitals detail structure from the software found in up to dated syllabus. This dz square, this x square y square, dxz. Okay. So what happened? The energy is comes higher. Thereafter, they are splitted. So you can find the interaction of the d orbital in 6-point energy xyz and xx minus yy minus zz minus axes are not same, and along the axis x square minus y square and z square will be destabilized more than the orbitals lying in between the axis. So you can find the energy here dx square or y square, the two orbitals, this is called Eg and this is called T2g, three orbitals in between. This energy is high, this energy is low. And when we come into this T2g and Eg, it is found that the energy difference is 10 dq in octahedral field, and it is found that dx square y square and d square have Eg are called Eg orbitals, and xy, xy, xz, or yz are the T2g orbitals. These differences are called in 3 by 5 delta 0 and 2 by 5 delta 0. Difference between T2g and Eg, we can have 10 dq or del 0. The conservation of barycenter from a spherical field to a octahedral field indicates T2g set must be destabilized as much as EG set is destabilized. Conservation of barycenter from a spherical field to octahedral field indicates T2g must be stabilized as much as the EG set is destabilized. With this example, with this details in background, the energy of an titanium T plus in water, we found it is a purple color, and the maximum energy in the visible spectra, we found that 20300 centimeter inverse, and the reference energy, if you want to get del 0, will be by, if you convert it by this formula, it will be 243 kilojoule per mole. So why this is so? Because titanium is a D1 system complex, and it is that the electron is in a T2g and it is in the Eg0, and the color is purple from where? For the excitement of T2g to Eg electron. And this is the electromagnetic curve present for this state in titanium oxide Ti3 plus. When we have more than one d orbital, that is T1 is a titanium is a D1 factor, D1 complex. Here is a more than d orbitals. We have D1 to D system, D1 to D3 system, T2 G3 Hund's rule of maximum multiplicity. For D1 to D3, no problem, because all that electron are in the T2G level. When we have more than 3 orbital electron, that is D4 to D7 systems, T2G may be T2G4 Eg1 and T2G3 Eg1, because when the field difference in between the T2G Eg is very strong, called low spin, and when the spin difference is very low, it is called high spin. This the field is weak. So two parameters are there. One parameter is high spin, and for parameter for the high spin and low spin cases is the CFSE, crystal field stabilization energy, dq and 10 dq, del 0 and 10 dq, and also the pairing energy of electron, that is repulsive energy. When we found that CFSE, crystal field energy del dq, is greater than pairing energy, so it is a low spin complex. It will be low spin complex like this. The low spin complex, all the electron in the lower energy level, and when CFSE is less than PE, then high spin complex, that is the electron is distributed T2G and Eg like this. And you can find this is the distribution D1, D2, D3, and D4. When there is a two option, it may be high spin, low spin. This optional D1. So from where you can find two factors are there, L0 and pairing energy. There is a pairing energy which is low, and delta is very high, L0 is very high, so becomes low spin complex. Therefore, there are two important parameters to consider. With this background of details, we found that two important factors we have to consider. First is pairing energy, which is repulsive energy. Next is Eg due to shifting, splitting, that is del 0, 10 dq. For both the high spin and low spin situation, it is possible to compute the CFSE. Here is a table you can find the del 0 and P, that is pairing energy, repulsive, pairing energy, repulsive energy, pairing energy or repulsive energy details you can find. We have taken D6 complexes system, FeO water as a ligand, and cyanide as a ligand. You can find for this del 0 is 10 for 0 400, and whereas by pairing is 17600. As a result, it becomes high spin because by pairing energy is very high compared to del 0. So they prefer to become high spin. Whereas if you take 32, when cyanide is added in the same configuration, 32850 and 1760, it becomes low spin. Okay, so when instead of this, if we go to cobalt system 3 plus, you can find cobalt fluoride 6 fluoride 3 minus, it is D7, cobalt hexaamine, it is D7. So centimeter inverse cases, you can find this is the difference 1300 centimeter inverse and 2300 centimeter inverse. So when their pairing energy is 2100, it is a deciding factor whether it will be high spin and low spin. You can find when the fluoride is a low crystal field value, so that is why it is giving you high spin, whereas it is low spin. Next, you can find del 0 is independent of ligand and metal. You can find the change in ligand and metal field will be due to chloride, H2, ammonia, and cyanide, and their energy is in centimeter inverse is given in this table, and also in kilojoule. This is the table, and also if you take another example of cobalt, rhodium, iridium, 5D, 4D, and 3D, it is found that the energy of 3D, 5D orbital are high, 4100. Next is 3400 and 2400. 800. So this is the del 0 is like this, and their ligand and metal complexes, ligand and metal cannot interfere in the value of del 0. It is provided nature, God provided uh, in between energy of a metal. You can find in this table, you can have taken ligand field splitting parameter of del 0 on ml6 complexes. When you have taken here chloride, H2, ammonia, diamine, cyanide, when it is D3 system, chromium 3 plus is 3700174415. So it is, so you can find with this increasing state, it is increasing. So this metal for D3 is increasing. So D5 Mn2 plus or Fe3 plus, this value is like this, increasing value. When we have taken D6 Fe2 cobalt 3 plus rhodium 3 plus, this value is like this. When you can find in this section, it is the increasing, this is the increasing value of crystal complexes of the ligands. When it is D6 nickel, we have taken, it is 750085. This is the value is taken, all the value is taken centimeter inverse, and in bracket they are all low spin complexes because their spin pairing becomes high. So in this table you can have a details of the ligand nature with the same metal or metal complexes or D5, D3, D4, their ligand value is increased. Next is dependence of del 0. It depends on nature of the how del 0 is responsible for different values, how we can get it. It has been found the nature of the ligands, nature of the ligand, and the charge on the metal ions. The charge on the metal ions. Metal ion ki charge hobe. Whether the metal is in 3D, 5D, or 4D elements, it depends on L0. So ligands, weak field ligands or strong field ligand depends on the character. For which one is weak field? We have taken in centimeter value 7,000 to 30,000, and greater than 30,000 is a ligand is called strong field, and the strong field gives us low spin energy. And this is called spectrochemical series, where increasing value of the different ligands have been found, that iodine is low compared to bromine, compared to sulfur, thiocyanate, chloride, nitride, fluoride, same urea, which minus oxalate minus H2. So H2 is a neutral ligand, and you can find the ligand is all the values are less. Okay. So it is not that the ligand in a negative charge or positive charge gives us the details of the strong fieldness of the ligand. Depends on the nature of the specific ligand we have get it. So carbon monoxide you can find highest, next is cyanide. So it is not that dependence on the charge on the metal ions. So you can find nature of the ligand, charge, and whether the metal in the key in which orbital is the key factor of the L0. And when we want to calculate the crystal field stabilization energy, the TFSE of the octahedral complex, we found that and T2G electron will give you minus zero point 0.4 type, and when you take an EG, it is zero point 0.6. Okay, so where T2G and T2G AG a number of electron occupying the respective labels. If CFSE is very large, pairing energy, that is CFSE is greater than pairing energy. So CFSE is very large. When CFSE is rather small, no pairing occurs, then pairing will be less than C. So this is the D system. We have a D1 system. You can find two types of crystal field theory will be there. And T2G number of electron in T2G is the number of 5 into zero point 0.4, and when we take this type of high spin complexes, this value will change. So T5 system had two type of crystal field energy, the octahedral complex. With this, come the close of the first topic, first series of the first topic of the crystal field theory of the series. Next to the next topic in the crystal theory. To everyone, thanks a lot.